In this lecture, we're going to be talking about something called the molar volume of a substance. By definition, the molar volume is the amount of space occupied by 1 mole of a substance. The name itself kind of says that. Molar refers to a mole, and volume, well, that's just what it says it is, volume. You may recall that in the last lecture, we assembled in front of you 1 mole of various substances. When we took a look at these moles, you probably noticed that each substance occupied a different amount of space. 1 mole of each of these substances occupied a different volume. I think the reason for that was fairly easy to understand. 1 mole of any substance is going to contain the same number of particles as a mole of anything else, namely 6.02 times 10 to the 23rd. But if the particles are larger, we would expect that mole to take up a greater amount of space. So common sense, if you wish, dictates to us that the amount of space, the volume occupied by 1 mole of any substance, should depend on what it is. I mean, it should depend on how big the molecules are. But there's one interesting exception to this rule. All the substances you saw on the table were solids or liquids. But for gaseous substances, something very interesting and surprising is true. 1 mole of any gaseous substance will occupy the same volume as 1 mole of any other gaseous substance under the same conditions. In other words, equal numbers of moles will take up equal amounts of space. Or put another way, equal numbers of molecules of different gases will occupy the same volume. If I could have assembled 1 mole of different gases on the table in the last lecture, and for some reason they wouldn't blow away or mix with the air, but would just sit there like solids or liquids, all the different gases would have occupied the same amount of space. Their volumes would have been identical. This idea was first proposed in the year 1811 by an Italian scientist named Amedeo Avogadro. It has come to be known as Avogadro's hypothesis. It says simply that at the same conditions of temperature and pressure, equal volumes of different gases contain the same number of molecules. Let's be sure we understand that. Maybe a picture will help. Let's take 2 equal-sized containers and fill them with different gases. Maybe I fill this one with nitrogen and this one with oxygen. And I put them at the same temperature and the same pressure, let's say room conditions. Avogadro's hypothesis says that these 2 volumes will, in fact, contain the same number of molecules. There will be the same number of dots in each picture. Now, if you're a critically thinking student, you might say something like, well, I guess I shouldn't argue with that. I don't think you're lying to me, and since this idea has been around since 1811, I suppose it must be true. But it just doesn't make any sense. How could equal volumes contain the same number of molecules when some molecules are bigger than others? After all, you can't put the same number of grapes and cantaloupes into the same size container. Well, there's an interesting and simple explanation for that. A gas is very different from a solid or liquid. In a solid or liquid, the molecules are very close together. That's why you can't put your fist through a piece of wood. You might be able to break a board, especially if you've had martial arts training, but I defy you to take your fist and put it all the way to a solid tree trunk. But you can easily put your fist through the air. And the reason you can do that is because air is almost all empty space. In fact, the air around you is about 99.9% empty. On a molecular level, if you think about it, that means that in a gaseous substance, there are tremendous distances between the molecules compared to the size of the molecules themselves. That's actually not easy to visualize, and almost impossible to represent graphically with any accuracy because the molecules are, in fact, extremely close together. A 1 cubic centimeter of gas at room conditions contains more than 10 to the 19th molecules. When you think about trying to stuff that many molecules into a 1 cubic centimeter cube, it's difficult to even imagine how you'll pack them all in there, yet alone have any empty space at all. But molecules are so tiny. Think of them as being almost infinitely small dots, that there still is a great distance between them compared to their size. A gas under normal conditions is about 99.9% empty space. So what does this have to do with equal volumes containing equal numbers of molecules? Well, if this gas is 99.9% empty space, then the size of the molecules really has almost no effect on the amount of volume that the gas will occupy. Now you might argue, but wouldn't it make at least a little bit of difference? I mean, if the red molecules were larger than the blue molecules, then wouldn't it make at least some small difference in how many molecules would fit in a given container? And the answer is yes. Careful measurements will show that Avogadro's hypothesis is only an approximation. Equal volumes of different gases do not contain exactly the same number of molecules, but it's so close that for all practical purposes, we can accept that hypothesis. So let's state the hypothesis again. Equal volumes of different gases at the same temperature and pressure contain the same number of molecules. Now, as we said earlier, you can reverse that statement. If equal volumes contain the same number of molecules, then the same number of molecules will occupy equal volumes. Well, there's a particular number of molecules that's very important in chemistry, the number of molecules in a mole, which we learned in a previous lecture is approximately 6.02 times 10 to the 23rd. So an interesting question to ask might be, what volume is occupied by 1 mole of gaseous molecules? How much space would 1 mole of gaseous molecules take up? There's actually no quick answer to that question because the correct answer is, it depends. And of course, you should ask, it depends on what? Okay, go ahead, I'm waiting. Thanks. It depends on the temperature and the pressure of the gas. Here's what we mean. If I take a sample of a gas and heat it, it will expand. The distance between the molecules will become greater. So at a higher temperature, the gas will occupy a larger volume. And at a lower temperature, it will occupy a smaller volume. And pressure also makes a difference. If I put gas into a container like a bicycle tire pump, where I can push down on the gas, increasing the pressure on the gas will compress into a smaller volume. So the volume occupied by a given amount of gas also depends on the pressure being exerted on the gas. So the question, what volume is occupied by 1 mole of gas, can only be answered after you specify the temperature and pressure you are going to use. Well, in order to communicate consistently, scientists have established what they call standard conditions of temperature and pressure, or STP. Unfortunately, there does not appear to be one universally agreed upon set of conditions. 2 different scientific agencies have used slightly different pressures as their standard. The small difference really doesn't impact what we're working on, so I'm just going to say that we'll be using the temperature and pressure shown on the screen. We will say that STP refers to a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. Most likely your textbook and/or teacher is using the same pressure of 1 atmosphere as being standard pressure. If you are actually using a slightly different pressure like 1 bar, it really won't make any difference for what we're doing here. But I did feel a need to at least mention this to avoid confusion. And if you actually have no idea what is even meant by a pressure of 1 atmosphere, don't worry. It's roughly equal to the pressure the atmosphere is exerting on you right now, assuming that you're near sea level and it's not too stormy outside. So at STP, we can now give a meaningful answer to the question, what volume will 1 mole of any gas occupy? It turns out that the molar volume of any gas at STP is about 22.414 liters, or stated more concisely, there are 22.414 liters per mole. Well, what does that mean? It's got to mean something, or we haven't really learned anything useful. Here's what it means. I just happened to find, sitting here, a box that someone left. It says this is 22.414 liters. Look at this box. Look at its size compared to me. Even though you can't handle the box to your TV or computer screen, you can certainly get a good feeling for how large a volume of 22.4 liters is. You can round the number off to 22.4 instead of 22.414, and that's fine. If you want to round the number to 22.4 when you work problems, that's certainly okay. Inside this box, if it were at STP, it isn't. But if it was, how many molecules would be inside the box? 6.02 times 10 to the 23rd. And it wouldn't matter what the gas was. 1 mole of any gas at STP occupies this volume. Well, now we're ready to add what we might call another parameter to our mix. In the last lecture, we worked several of what we call mole problems. And when we were working the mole problems, the only quantities we were dealing with were grams, molecules, and moles. And we converted grams to moles and molecules to moles and moles to grams and moles to molecules and back and forth. Now we add another parameter to the mix. And here you begin to see the advantage of establishing the kinds of understandings that we talked about in the earlier lectures. If you have no idea what a gram is or a mole is, or what is meant by 58.5 grams per mole or 6.02 times 10 to the 23rd molecules per mole, if you have just been memorizing formulas or using some method to solve problems, then at this point there's a danger that everything becomes just a hodgepodge of units and every problem is different. But if you've held grams and know what they are, and you've measured volumes and measured them, and you measured them well, and you have a good feeling for volume, and you've thought about what is really meant by the different this per that's, like 18.0 grams per mole and 6.02 times 10 to the 23rd molecules per mole, then everything begins to fall into place. Every problem becomes just one problem, or perhaps at most 3 different problems, like the students in rooms problems. And for the remainder of this lecture, we're going to work several different mole problems. But they really aren't different problems. They're all the same kind of problem, just involving different kinds of things and units. Now, before we start working problems, I'd like to re-emphasize the fact that the 22.414 liters per mole is not something that you can apply anywhere. You know, like 6.02 times 10 to the 23rd molecules per mole. 6.02 times 10 to the 23rd molecules per mole applies to anything under any conditions. It is always true. 22.414 liters per mole can only be applied in a very specific instance. Only when you are talking about gases and only when they are at STP. It isn't true for liquids or solids. When you looked at those solids and liquids in the last lecture, they didn't occupy a volume equal to the big box you saw earlier in the lecture. And it isn't even true for gases when they are not at STP. Now, in the problems we're going to work from now till the end of this lecture, there will potentially be 4 possible quantities involved. We'll talk about the moles of the gas that we have at STP, the grams of the gas, the molecules of gas, and the number of liters. There are 3 this per that's. One is grams per mole. That, of course, is the molar mass. That's different for every substance because some molecules are heavier than others. Another is molecules per mole. That's the same for any mole. It's always 6.02 times 10 to the 23rd molecules per mole for any substance. Doesn't depend upon what it is. And now we've added a new this per that, liters per mole. That's a meaningful quantity only for a very special case, when you are talking about gases and the gases are at STP. When these two conditions are met, we can say that there are 22.414 liters per mole, but again, only for gases and only at STP. With these things in mind, we're ready to look at some problems. Again, the purpose here is not just to get the correct answers, but rather to think about the quantities and the relationships involved. Read the problem several times if necessary, stop the video. Draw a picture if necessary, and see if you understand these quantities and the relationships well enough to put the numbers together in the problems in the natural way that they would have to go together. Our first problem is, how many moles of carbon dioxide, CO2, are contained in 65.5 liters of CO2 gas at STP? Now this problem wants to know how many moles of carbon dioxide gas I have if I have 65.5 liters of this gas at STP. How should we think about this? We're trying to find out the number of moles from the number of liters. There's absolutely nothing in the problem that involves grams, so there shouldn't be any need to calculate the molar mass of CO2. And there certainly is nothing in this problem that talks about molecules, so we don't need to use 6.02 times 10 to the 23rd molecules per mole in this problem. The number that's important in this problem is 22.414 liters per mole. For any gas at STP, and in this problem we do have a gas, carbon dioxide, and it is at STP, there are 22.414 liters per mole. Going back to our box, this would be 1 mole. This is 22.414 liters. But I have 65.5 liters. That's a much bigger box than this. Do I have more or less than 1 mole? Well, if you look and think about these quantities, hopefully you will quickly realize that you have to have much more than a mole. In fact, you may quickly compare these two numbers and see that you appear to have a little less than 3 moles. But since teachers always want the actual numerical answer, we'll do the arithmetic. 65.5 liters divided by 22.414 liters per mole means that I have about 2.92 moles of CO2 gas. Let's try another. How many moles are contained in 18.0 liters of SO2 gas at STP? This problem is just like the last problem with one small difference. I only have 18 liters of sulfur dioxide gas, but it takes 22.414 liters to make a mole. So I know that I have a bit less than 1 mole of SO2 gas. Specifically, I have 18.0 liters divided by 22.414 liters per mole, which comes out to about 0.803 moles of SO2. And once again, note that there was no reason whatsoever to calculate the molar mass of SO2 since there was nothing in the problem that involved grams. And there was no reason to bring in Avogadro's number, 6.02 times 10 to the 23rd, since there was nothing in this problem that dealt with molecules. And another. How many liters are occupied by 3.44 moles of CH4 gas at STP? Now this problem is not, quote, just like the two previous problems. But you know something? Maybe it really is. It's just the same stuff. Moles, molecules, and liters. And a few this per that's like grams per mole, molecules per mole, and liters per mole. Sure, there's lots of different combinations, just like I could make up different kinds of students and rooms problems. But none of them were difficult when we knew what we were talking about. We know that 1 mole of CH4 gas occupies a volume of 22.414 liters. Think of that box. And here we go again. If 1 mole occupies 22.414 liters, then what volume would 2 moles occupy? Well, twice as much, of course. And 3 moles? 3 times as much. And 3.44 moles? Well, just 3.44 times as much. So we multiply 3.44 moles times 22.414 liters per mole to get our answer of about 77.1 liters. And another. What volume is occupied by 0.823 moles of oxygen gas at STP? In this problem, I have less than 1 mole of oxygen. This means that I am going to have less than 22.414 liters. I will have some fraction of that volume. Specifically, I will have 0.823 of that volume. And 0.823 of a mole times 22.414 liters per mole gives me a volume of about 18.4 liters. And another. What is the mass of 5.62 liters of N2 gas at STP? Now, this problem is much more challenging. It would not be surprising if you had a little difficulty with it. There actually is more than one correct logical way to think through this problem. I can immediately think of two that would kind of fit the types of logical thinking that we have gone through in the past. If you solved it by a slightly different approach than the one I'll present, that's fine, just so long as you thought through the problem logically and understood what you were doing. Here's one way of thinking through the problem. You're given the volume of nitrogen gas at STP and asked to find what the mass of this is. Now, none of the this per that's that we've talked about in the last few lectures will directly convert liters of a gas to grams of that gas. But since the problem asks for grams of the gas, we almost certainly are going to need to know the molar mass of nitrogen. Nitrogen gas weighs 28 grams per mole. Now, how am I going to get from liters of nitrogen gas to a mass? Maybe you can do that immediately and quickly, but if you can't, let's use that little trick that we talked about. It often helps to think of a problem backwards. If I have to find the number of grams, what might I have calculated just previous to the last step that finds the number of grams? Well, the number of moles. If I knew the number of moles of nitrogen gas I had, I could easily find the number of grams by multiplying the number of moles by what 1 mole weighs. But how can I find the number of moles? That's just the kind of thing we did just a few minutes ago. So this is a two-step problem, but it's two very simple steps. By working backwards, I can now work forwards. I have 5.62 liters of nitrogen, which is less than a mole. 5.62 liters divided by 22.414 liters per mole means that I have 0.251 moles of nitrogen gas. Nitrogen gas weighs 28 grams per mole, so if 1 mole weighs 28 grams, then 0.251 moles will weigh 0.251 of 28, or about 7.03 grams. And another one. What volume is occupied by 34.8 grams of C3H8 gas at STP? Now, you probably noticed that every problem is a little different. You can't just, quote, repeat what you did in the last problem. And I hope you're beginning to realize that trying to memorize a specific method to solve each type of problem would be well on its way to being an impossible task. You would either have eaten or soon would be eating the orange fruit. Now, if you don't know what that means, look at Lecture 1 again. But these aren't all different problems requiring that you memorize a different approach for each. Something like, in this kind of problem we multiply, in this one we divide. This is a two-step problem. We have to do this first and then this. This is a different two-step problem. First we do a different thing and then we do a different thing still. There really is only one problem, in a sense, if you understand and have a good mental picture of the quantities you are dealing with. In this problem, I have 34.8 grams of the C3H8 gas, and I'm supposed to find out what volume it occupies. Perhaps, again, you can see your way from the beginning to the end of the problem immediately. And if you can, that's great. But if you can't, here's the trick. If I want to find the volume of the gas, what's the last thing I'll probably do? Well, since I know that there are 22.414 liters per mole, the last step would be to multiply the number of moles of the gas by the volume occupied by 1 mole, namely the 22.414. But they didn't give me the number of moles, they gave me the number of grams. But that's simple. I know how to convert grams of something into moles. all I have to do is take the number of grams I have and divide that by how many grams it takes to make 1 mole, in other words, the molar mass. Since the problem starts with grams, I know I'm going to need to calculate the molar mass of C3H8. That comes to 44.0 grams per mole as shown on the screen. I only have 34.8 grams, so I'll have a little less than 1 mole. 34.8 grams divided by 44.0 grams per mole means that I have 0.791 moles of C3H8. Now I have to find out what volume that would occupy. There are 22.414 liters per mole of any gas at STP. Since I have less than a mole, my answer must be less than 22.414 liters. Specifically, 0.791 moles times 22.414 liters per mole comes out to be around 17.7 liters of C3H8. Now, if you've solved these problems correctly, I think you really understand these concepts, but let's try another. How many molecules are there in 74.0 liters of Cl2 gas at STP? This problem is a little different from all the others we have worked. Once again, the idea is you could find the number of molecules if you knew the number of moles, since we know that there are 6.02 times 10 to the 23rd molecules in 1 mole. And we can find the number of moles since they give us a number of liters of the gas. And we know that there are 22.414 liters per mole for all gases at STP. So it works out like this. 74 liters divided by 22.414 liters per mole means that I have 3.3 moles of chlorine gas. 3.3 moles times 6.02 times 10 to the 23rd molecules per mole gives me about 1.99 times 10 to the 24th molecules of chlorine. And another. What volume is occupied by 7.26 times 10 to the 21st molecules of N2O gas at STP? Here I'm asked to find the volume. Again, thinking backwards, I could find the volume occupied by the gas, the number of liters, if I could find the moles, since I know that 1 mole would occupy 22.414 liters. But how can I find the number of moles? They didn't give that to me. They gave me the number of molecules. Well, what relates molecules to moles? Answer, there's 6.02 times 10 to the 23rd molecules in 1 mole of anything. In fact, if I wanted to compare these two numbers, I might be able to see that I have less than a mole, although this comparison is a bit more difficult since we're dealing with exponential numbers. So 7.26 times 10 to the 21st molecules divided by 6.02 times 10 to the 23rd molecules per mole means that I have 0.0121 or 1.21 times 10 to the minus second moles of N2O gas. Now that I know the number of moles, I can find the number of liters, since I know that 1 mole just occupies 22.414 liters. Therefore, 1.21 times 10 to the minus second moles times 22.414 liters for 1 mole gives me a volume of 0.271 liters. And one final problem. What is the mass of 5 moles of O2 gas at STP? I purposely ended this lecture with what might be called a trick problem. Because I said this was a gas at STP, you may have been very tempted to grab the number 22.414 liters per mole, since this is a number that we usually need to have when a problem talks about a gas at STP. But that was just to throw you off. This was actually a very simple mole problem. Oxygen gas has a molar mass of 32 grams per mole. 1 mole weighs 32 grams. So 5 moles would just weigh 5 times as much. 5 moles times 32 grams per mole would come to 160 grams of oxygen gas. In the next lecture, we're going to take a slight detour and look at 2 kinds of classic chemistry problems: percent composition and empirical formulas.